All right. So we have Daivik, Sahib, and Arush in the class as well. Some kids are still missing. What happened to you guys yesterday?
Oh, his birthday was yesterday, so we went to
Oh.
his birthday.
Yeah. So this week and next week, that's where I have assumed flexibility from everybody because this Saturday is my daughter's Aringithram event, and then next Saturday I'm going to Houston for my daughter's college admission. So that's why I said okay, fine. This week and next week we'll do class on Tuesday and Thursday, and then we'll go back to normal schedule.
Okay. Oh yeah, I won't be here this Thursday because I'm going to NC.
Oh, okay.
So yeah.
Just say no.
Okay. Then you have no other choice but to give me one extra view on my video.
Okay.
All right. So let's get started. What are we going to learn today? Anybody wanting to make a guess based on what I put in the WhatsApp group?
I'm not in the WhatsApp group.
Yeah, in WhatsApp group. So then all of you who have your own number in WhatsApp group, you will have direct access to the information. Some of you who don't have it, I would request keep checking with your parents. Okay, what is that is going to be covered today. You can check it offline. I mean, it doesn't hurt. And even if you don't get to know about it, fine. I mean, we are going to learn it. That message doesn't do any wonder for any of us. All right. So we are going to talk about permutation and combination, which is what we started in the last class. Are you guys feeling hot? It's okay. Otherwise, I will turn on the AC. Somehow I chose to wear this t-shirt, which is pretty hot, but we'll manage. So we are going to talk about permutation and combination. Now, let's start from the basics and then we'll go to how do we actually use these concepts for doing more fun stuff. Arush and David, do you guys want my mind shifting a little bit so that Arush is always visible to me? Okay. Yeah. And this is the comfort factor I have. When I see you guys, I can make out whether I'm making sense or not. Okay, so permutation. What is your understanding of permutation? I mean, what does it mean actually? Any weird thought? It's okay.
It's hard to define.
Give an example. If you can't tell that in English, tell me with some example. Om, Shiv, Dev, anybody here in the classroom?
I'm pretty sure permutation has to be in order, right?
Mm-hmm.
Okay.
Permutation is where order matters. Combination is where order doesn't matter.
Okay. Shiv, Om, Dev, do you guys want to give any initial thought?
It's like every possible combination in order specific.
Is it the number of digits you think?
Oh, okay. Okay. I heard some of you saying something which kind of gives me the clue. At least I'm not blindfolded right now. Let's look at this. Now you guys will enjoy my drawing skills. Okay, this is one chair. Something looks like a chair. This is second chair, and then I have, let's say, third chair. If I have 3 chairs, I can apparently make only 3 people sit, right? Unless I'm forcing 2, 3, 4 kids on one chair. Yeah. So I have 3 chairs. At best, 3 people can sit on this. Yeah. That is not permutation. Now I have 3 people. Let's say somebody with name A. Let's say A stands for Aniket, B stands for Biren, and C stands for Chandrachud. That's one of my uncle's name. Okay. So A, B, and C are 3 people who can be made to sit on one of the chairs. Now, let's say if I put A on this, or let's think about how do I want to fill these chairs. I have 3 options. Let's say this is chair 1, this is chair 2, and this is chair 3. Okay. If I want to decide how many ways I can make people sit on chair 1, how many options do I have? 3? A, B, or C? One of the 3. So when I have 3 options for chair 1, let's say I randomly picked one of the person, be it A, B, or C. I picked one person. Then when I am going to chair number 2, I have only consumed one of the person. Okay. Let's say I picked a B for this chair. Okay. Now, what are the options that I have for chair 2? Two options. I can pick either A or I can pick C. Let's say I picked A for this chair. So here I have two options, A or C. Let's say I picked A for this chair. Let me make the A sit on the chair. Okay. Now B is sitting on chair 1, A is sitting on chair number 2. How many options I'm actually left with for the third chair?
One.
Only one option. And I cannot do any more juggling. I have to make person C sit on this one. This storyline looks okay so far? Dave, Save, everybody? Okay. Now, so here, what is the only option I had? B and C? No. We had multiple options. Now let's look at what are the different options I had. Let's say when I made chair A get filled by B, I had this chair, I had option A and C, or first being filled with B, I had C and A. So that's what I meant by two options for second chair when first one is filled with B. Correct? Are you guys with me so far? Everybody? Now, when I chose B as the option for first chair, I got two options here, AC or CA. When I picked B, A as the first chair option, I had B or C, or I had C or B as my two options. When I picked C, I might be getting you guys a little tired right now, okay? And that's not the intent. I'm just trying to make you guys go deeper inside this one, okay? So when I chose C as my option for the first chair, I was left with A and B for the second and third chair, or B and A. These were the options I had. Looks okay? Convincing? Okay. So if you look at all these options, what is happening? First chair is taken by B, second is by A and C. In the second option, first remained the same, we only suffered between these two. Similarly, for the second case, when I fixed first chair with A, I could shuffle between these two. What I'm trying to convey here is that here whether A is sitting on the second chair or C is sitting on the second chair for the first two options matters. Okay? Let's say on the second chair, whoever sits on the second chair gets a $10 prize. It matters. A and C will not do some arm wrestling to figure out who sits there. So basically what I'm saying is, when you have, let's say, certain options to fill, and the order between the way to fill was important, that is when it is called permutation. Okay? So the different ways you can organize certain things, and when the order between them matters, that is called permutation. Is that okay? Yeah? Okay. Now, so I said we are going to learn permutation and combination. So we have just learned permutation. What I said was, if the order matters, that is permutation. If the order doesn't matter, it's combination. Yeah? And we'll look at some examples. We'll do a deeper dive into it, but this is just a starting point. If somebody says, okay, what is permutation and combination? This is the first and the foremost important difference between the two. Yeah? Now let's continue with our journey. Let's forget about the English part of it. So we had 3 chairs and we had 3 people to fill that with. And what we saw was we had 6 options. Is there a 7th option that you guys can think of? When the order matters, is there something that we are missing? The only precondition here was that we are not repeating something. I mean, we cannot repeat. We cannot have person A sitting on this chair and person A sitting on this chair also. Right? So, we don't have the option to repeat. At the same time, the order matters. So, considering that, what we are seeing here is there are 6 options that we came to. Now, this is another way of looking at it. Now, first chair, you had 3 options. Second chair, you had only 2 options. After you consume the first part, you had 2 options to play around with. And when you consume the first 2 slots, you had only 1 option. What it is translating into, see, 3 into 2 into 1 is what the number of options that you see here. Yeah? So tomorrow, if somebody says that you have, let's say, 4 apples, or 4 fruits. Let's say fruit 1 is apple. I don't know if it looks like apple, but let's assume that. Second one is orange. Third one is banana. Fourth one is watermelon. Okay? And you have 4 kids. What are different ways you can distribute? It's as good as the chair option that we saw. If you are giving, when you are picking the first fruit, you had 4 kids. When you are picking the first fruit, you have 4 options to choose from. For the first option, for the first kid, you had 4 options. For the second option, after the first kid got its fruit, then you were left with only 3. After these 2 kids were given their choices, third one you were left with 2, and then 1. And when you kind of do that breakdown of different options, by looking at the combination, you will see that it translates into this many options. This is the starting point for permutation, and this is what introduces us to a new term called factorial. Now, is it okay so far? Save, Dev, Om, yeah, okay. Arush, no problem so far, beta? No? So what we are deriving from what we have seen so far is that if you have certain number of options, let's say, let's stick to the chair option for now. 3 chairs and 3 people to be sat, or 3 people to be made to sit on those chairs. You can see that you are talking about first chair 3 options, second chair 2 options, third chair 1 option. And the total number of permutations that we are coming across is going to be 3 into 2 into 1. And this is given a name, factorial. So tomorrow if you have, let's say, for 1, 2 or 3 chair, 1 or 2 or 3 options to choose from for that many people, it's easy. You can always look at different permutations and arrive at it. What if you are going for a party where you have 100 guests and you have 100 chairs? And then you have been given the task of finding out what are different ways you can organize them. If you have to think of 100 numbers, think of how big a board you would need for figuring out the combinations. Instead of doing that, now just because we are seeing with 3 people in 3 places, you can organize them in factorial 3 ways. And factorial 3 is nothing but 3 into 2 into 1. Likewise, if you have 5 people to arrange in the 5 places, you say, okay, fine, I can extrapolate that knowledge, and that becomes factorial 5, which is nothing but 5 into 4 into 3 into 2 into 1. And any factorial, what it means is, it starts from that number, keeps decrementing by 1 number until it goes to 1. Is it getting anybody stressed out? Except me. Okay. So this is a factorial understanding. So now, any factorial, let's say somebody says, okay, what is the value of factorial 7? You'll say, okay, I don't really need to worry about it. I'll start from 7, keep decrementing by 1 at every step till I reach 1. Okay? So this is the factorial part. So you have 5 options, 5 people to choose from. This is what it turns out to be. But let's look at some classic examples that will kind of make us relate these concepts with the actual problem that we'll come across. Let's look at one of them. Let me read one problem for you guys, and then we'll see how much sense it makes. Before we go to the problem, let's look at one more concept. We talked about permutation. I said 3 chairs, 3 people. It's okay. Now you are playing musical chair. Okay? And you have 7 people, let's say, participating in that event. Okay? and you have only 3 chairs. How many ways you can arrange 7 people on 3 chairs? And don't think of any formula, just think of practical situation. So if math doesn't help, use your visual or optics for thinking about it. Okay, so this is, let's say these are chairs. I have 3 chairs. Okay, these are 3 chairs. And I have 7 people. How many ways I can make them sit on these 3 chairs? Om, Shiv, Dev, Sahit. Okay. Don't assume that you guys are grown up. Assume that you are a child. Okay. I mean, you guys are a child for me anyways. Here, first chair. How many options you had? 7, right? So for filling the first chair, you had 7 options. Yeah.
It's like 7 factorial. No. It's
No,
like
it's in
3
stops.
I'm not going that fast. I'm going slow.
It stops at
7
Stops
factorial
us.
till 5.
7 factorial till 5, actually, you're thinking in the right direction, but you're not representing it right. I'll come to you. Okay? So, first, for filling the first chair, we had 7 options. Do you guys all agree? Om, Dev, Shiv? Yeah? Simple, right? No complication. After I fill the first chair by choosing one of the 7 options, how many options I had for the second chair?
6.
Yeah? If after I fill the second chair, how many options I was left with? 5. And that's where life ends. No looking beyond this. So you had first chair to be filled in 7 possible ways. Second chair you could fill in 6 possible ways. And the third chair you could fill in 5 possible ways. Given the situation where you had 7 people to occupy 3 chairs. And these were the 3 options that you could think of. So total number of combination that you're talking about is this many. Is that making sense? Shiv? Dev? Yeah?
Yes, sir.
Okay. But what happened to our factorial thing? We just started with that and that disappeared. But before we go back to factorial, this is still aligning with our understanding of permutation, where permutation says that they are the ways you can arrange things when the order matters. Here the order is mattering, right? If I pick the first place among one of the 7 options, then I'm left with remaining 6 only to juggle with for the second place, and then that thing continues. So 7, 6 or 5, that the 7 into 6 into 5, that was the number of options I had. Let's assume we had 4 chairs to be filled. Then the 4th chair could have been filled in 4 possible ways, and the total number of permutations we had were 7 into 6 into 5 into 4. Is this okay so far? Yeah? Now, let's extend this. Is that your car? Anybody's car? No? That's my neighbor. We're just poking. Okay. So, here, for 7 people to be made to sit on 4 chairs, these were the number of permutations we had. Now, what is that we are seeing here? For 7 people on 4 chairs, I have this many permutations that I can do. What we are missing here is 3 into 2 into 1. And let me put that in a different color so that it gets our attention. This is what was missing and keeping us away from the factorial thing, right? 5 people in 5 places, factorial 5 ways. 3 people, 3 places, factorial 3 ways. 2 people, 2 places, factorial 2 ways. 1 person, 1 place, factorial 1. That is only 1, yeah? So this red thing is what was missing. This is a red line, red mark. So, okay, fine. Whatever was missing, I added them. let me put it here also. So when I was trying to fill 4 positions with 7 options, this was the number of options I had. I had these many permutations that I could think of. I just appended these things so that it gives us some direction or it gives us some way to correlate that with the factorial thing. So now what I have here is this part becomes 7 factorial and this becomes 3 factorial. And what is the correlation between these two?
They both have 3 times 2 times 1.
Not these two. I'm saying what is the correlation between what we saw now versus the actual question we had. We were trying to fill 4 positions with 7 options. This is what we got to.
It's the same thing.
A little bit more. Yeah.
Wait, no, wait. It is.
It's the same thing. Value is the same thing. I'm saying, how do we derive some interpretation out of it? It is not looking like whatever was the number of options I had. Yes.
When you're dividing that 3 to 1, go away on both sides. Yeah.
Both will go away, right? So I'm just trying to convert this understanding into some generic form. Okay?
Oh, it's also 7 minus 3.
7 minus 3, correct. So it becomes factorial 7 divided by 7 factorial. I studied in Hindi board where we used to call it factorial 7, but when you are saying in English, you say 7 factorial. So if I use factorial before or after, don't worry about that. Okay. So here, this is nothing but 3 is nothing but 7 minus 4 factorial. Now you can relate this with this. So when you have certain number of options to choose from for filling certain places, you can have this many permutations, which is factorial of the number of options divided by factorial of this minus this difference. Now you will say, sir, you are getting us confused. And that's a fair point. That was not purposeful. We are still trying to digest this. So again, even if you don't get to this formula, it's okay. Your underlying concept remains the same. You are looking at what are different options for filling each and every position, and then you're multiplying them. Up to here is what you need. Whether you're multiplying, dividing there or not, whether you're converting to this form or not, that is just an extension of the base concept which remains this. Is that okay for everybody? Now comes the magical part. So this is what is called a formula for permutation, which we just derived based on what we had learned or understood. So it says NPR, permutation of n options with this many positions to be filled will be equal to factorial of n divided by factorial of n minus r. Now let's go back to original concept, okay? I know I might be sounding a little cryptic right now, but let's go back to our original concept. We had 3 chairs and 3 people. What we found out is you can make them sit in 6 possible permutation ways or factorial 3 factorial ways. Let's see here. 3 people, 3 chair. Okay? I'll put 3 people, 3 chair. How many permutations I'm talking about? I'll apply the same formula. This becomes factorial 3 divided by 3 minus 3 factorial. This becomes factorial 3 factorial divided by 0 factorial. 0 factorial is given a value of 1. So, if you have 3 options to fill 3 places, you can do that in factorial 3 ways. If the number of options and number of things to consume are not the same or the same, you can always apply this formula, because this formula is derived from the same understanding. You have this many options and this many things to fill. You said, okay, first one this many ways, second one this many ways, third one this many ways, fourth one this many ways. This is my total number of options. You just generalize that and you got to this formula. And that became a generic formula for us that we can follow. If we remember the formula, if we don't remember the formula, it doesn't hurt. We can still go back to the original base method from understanding point of view and we can still solve it. It will give us the same answer. Yep.
Why is 0 factorial 1?
Why is factorial 0, 1? So now, this is what mathematicians wanted to kind of come to an agreement. Now let's look at it. So that was one of the topics that I wanted to cover. So if I'm saying any factorial, let's say n factorial, I'm talking about n multiplied by n minus 1 multiplied by n minus 2, and I will keep going down till I reach 1. Yeah, that's how factorial n means. Steven, Dave, Om, everybody with me? Now if I say factorial 4 factorial, I'm talking 4 into 3 into 2 into 1. Okay? When I say factorial 2, I'm talking about 2 into 1. Okay? If I'm talking about factorial 1, and the idea is it's to start from that number, keep decrementing till it reaches 1. So 1 itself is 1, so you cannot decrement, that becomes your 1. Now 0 factorial, why it is 1? Why it is 1? The answer lies in this whole thing that we just talked about. If I have 3 places to be filled by 3 options, or 3 options I have for filling 3 positions, we can do that in 3 factorial ways. That's what we saw. And if we apply that to the generic formula that we realized, 3 out of 3 options, it becomes 3 factorial divided by 3 minus 3 factorial. If you relate this is 0. So this generic approach tells you that you should not assume. See, this is not given as a rule of physics, right? Where you see it happening. This is what mathematicians agreed to. Say, okay, fine. If I'm coming to this as a generic formula, this is my only exception where I see that if the number of options and the number of things that I'm juggling with both are matching, in the most practical way I see it is just that factorial. But if I apply that in this formula, this becomes 0. So let's agree to make this as 1, and that is how they took it forward. So these are basically complementing each other. Okay, is it making sense? No.
And then is there negative factorials?
There is nothing called negative factorial because you are stopping at 1, and it always decrements. If you say negative 3 factorial, if you decrement negative 3 by 1, you go to minus 4. Then you go to minus 5. You are never going to reach 1. The basic premise of factorial says you will decrement that number till you reach 1. If you are picking up a negative number and then you are decrementing it, by no means you can reach to 1. 1 as in positive 1. Okay? So there is nothing called negative factorial. And factorial is a special thing that is understood or picked up as a concept only from permutation and combination standpoint. It's not used anywhere else. Okay? Now, all this is theory. Let's forget about everything right now and look at some of the simple sample problems that you guys will come across, and then we'll see how is our understanding helping here. Okay? Is everybody okay to go to a problem, a legitimate problem, rather than any cooked up problem from my side? Okay, so let me read a problem and pay attention to what I'm saying. In one game, okay, sorry. In one game, a code made using different colors is created by one player, the code maker. In one game, a code made using different colors is created by one player, the code maker. Okay, somebody who's given a designation of a code maker is creating a code using different colors. Okay, and the other player, the code breaker, tries to guess the code. The code maker gives hints about whether the colors are correct and in the right position. The possible colors are blue, yellow, white, red, orange and green. How many 4 color codes can be made if the colors cannot be repeated? Loaded one?
How many colors are there?
Okay, so let me read the question one more time. It's a word problem, right? You cannot skip any part of the word problem. In one game, a code made using different colors is created by one player named code maker. Okay, so the code is created by using different colors by somebody called code maker, and there is somebody called code breaker who tries to guess the code. Meaning, every code is a combination of colors. That's what it's saying. The code maker gives hint about whether the colors are correct and in the right position. Okay, so the code maker who has made the code using different combination of colors gives the hints about whether the codes are correct and in the right position. The possible colors are blue, yellow, white, red, orange and green. Blue or yellow, white, red, orange and green. How many 4 color codes can be made if the colors cannot be repeated? Yeah.
Yeah, there's 6 colors, right?
Yeah.
Then 360 options.
Okay. So don't give me the answer. Tell me how you came to that.
So as you learned before,
Mm-hmm.
you gotta do the formula thing. So n for number of options there are, so there's 6 options, and
Mm-hmm.
factorial, and over, and against the 6 minus list of options, which is 4, and then
Okay.
factorial that. And if you do that, you get 360.
Okay. Yeah. Yep, Davik, you were saying something.
I was saying what we were saying.
Same thing. Same thing. So, okay. Dave, Om and Shiv. Any thoughts? Did you guys hear the question clearly?
Yes.
Yeah.
What would be your thought process around this question? I mean, how would you try solving it? What did you understand from the question and what is the approach that is coming to your mind?
So there's 6 colors
Mhm.
and there's 4 spots for the color.
Mm-hmm.
So that means you would have 2 left, right?
Mm-hmm.
2 colors left. So then that factorial would be in the denominator, and the factorial of 6, because that's the total, that would be in the numerator.
Mm-hmm. So you're saying it will be factorial 6 divided by factorial 2. Is that what you're saying? Okay. Save. Okay. Now, see, you guys are probably grasping this concept very quickly. I have never been that intelligent, trust me. Now, let's look at it. Let me read the question one last time, okay? The question says, now I'm trying to solve it, okay? In my own lame way. In one game, a code made using different colors is created by one player, the code maker. Okay, somebody is creating the code using the colors. Okay, and the other player, the code breaker, tries to guess the code. Okay, fine. The code maker gives hint about whether the colors are correct and in the right position or not. So basically, position matters here. This is my takeaway. The possible colors are blue, yellow, white, red, orange, and green. How many 4 color codes can be made in the color if the colors cannot be repeated? So here there are a couple of things. There are 6 colors to choose from and they are all different, thankfully. And the code is made by combination of 4 colors. And the other clue that is given is the colors cannot be repeated. So I cannot have green, green or white, white coming twice or 3 times or 4 times. So we are choosing unique combination. It's as good as making 6 unique people sit on the 4 chairs. Correct? Now, this is my first color. So the code is made of 4 colors, right? This is how the code looks like. I have 6 colors, 6 unique colors. So it is all about first color box I can fill in 6 ways. Second color box I can fill in 5 possible ways. Third color box I can fill in 4 possible ways. And fourth color box I can fill in 3 possible ways. This is what will be my answer. And you can also, since we have looked at the permutation formula as well, and it says, okay, fine, I have 6 options to find out permutation of 4 things. So this one gives me 6 times 5, 30 times 4, 120 times 3, 360, like most of all of you said. Or if I fill in this formula, it gives me factorial 6 factorial divided by 6 minus 4 factorial. Both is going to result into same thing. Factorial 6 will give you 6 times 5 times 4 times 3 times 2 times 1. And factorial 6 minus 4 is 6 minus 4 factorial is 2 factorial, which is 2 into 1. This knockoff, this knockoff, 5, 6, 5, 4, 3. Same thing. So basically, if you look at this formula versus this understanding, both are the same thing. This is just a more generalized way of doing it. Okay. Just because we are talking about things that we can calculate manually, so we can use that approach also, because that's our core concept. This is just a way to represent. Okay. When your number becomes bigger, you don't want to grapple with this by doing bigger calculation, right? If you're talking about a code made of 50 colors, and you had 80 colors to choose from, are you going to enjoy doing that calculation that way, or you would simply apply that generic formula to do it? But the good thing here is you don't have to memorize this. You can always go back to the basic concept. Just as a human, if you try solving a problem, this is how you will realize. Does that make sense, Shiv, Dev, Sahib? Yeah?
Yes.
So, what I'm trying to say here is, even if I tell you guys that there's one thing that we did not talk about. When we talked about the code, again, why we went for permutation? Because the order matters. Green in this box versus this box versus this box versus this box matters. Your yellow, white, green, red is different from red, white, green, yellow. So that's why this order matters, right? It's a code. If somebody has to decode it or hack the system using the color, if you change the kind of order of the colors that you have selected, you will not be able to decode it, right? So it's a classic example of permutation where the order matters. That's why we went for this option and we looked at the permutation formula. Yeah, we had 2 options to choose from. Is everybody with me? Yeah. Okay, let's look at one more problem, because more the problems we deal with, the problems will not remain a problem anymore. Okay. Second problem, I will let you guys, again, we'll not try solving each and every problem that we come across. I'll just try getting your approach basically. A club of 9 people wants to choose a board of 3 officers, president, vice president, and secretary. How many ways are there to choose the board from 9 people? Reading the question one more time. A club of 9 people wants to choose a board of 3 officers, president, vice president, and the secretary. How many ways are there to choose the board from the 9 people? Don't try solving it, tell me what the approach would be. Yeah.
Okay, so it's 3 people, that means 3 positions, and there's 9 people. So that means automatically you can get the answer just from that, because it's just you just count them 3 times. 9 is to 8 is to 7.
Yeah. That's the easy one. Or if you remember the factorial formula, permutation formula, you can apply there. Both will get you the same answer. Yeah. Om, Shiv, and Dev, did that question make sense?
Yeah, I got the answer.
Yeah.
I mean, it would, from the formula that we use, you would get 9 factorial over bracket 9 minus 3 bracket 5. factorial, which would be 9 factorial divided by 6 factorial.
Right. And again, at times you might want to keep it as simple as you want. Nobody is insisting us to use the formula. You will just look at it in a very simple way. Okay, nine people, 3 positions. Okay, first position I have 9 options. Once I have picked one person for the first position, I'm only left with 8 people. Once I picked up the second position also, 2 people are gone, I have only 7 options. Multiply them, you're right. So, I mean, you can always choose whichever works for you faster, depending on what kind of calculation we are dealing with. Yeah. Let's look at one more problem. Neha is playing a word game where she is trying to make 3-letter words using letters in the word tiger. She cannot use the same letter twice. How many unique ways are there to change 3 ways to arrange 3 letters from the word tiger? Does it look complicated?
No.
No. Do you want to waste your time?
No.
No. Okay, let's move on. So, everybody is on the same page, right? Nobody is wanting to waste time? Okay, good. What is that?
I said I got it instantly without a calculator.
Yeah.
It's easy.
No, and see, we have made calculators. Humans have made calculators. Calculators have not made us. So we are smarter than calculators is what we have to keep in mind. Okay? Let's move on. I have one more problem. A card game using 36 unique cards. 4 suits, diamond, hearts, clubs and spades. So a card game using 39 unique cards, which is comprising of 4 suits, and, diamond, hearts, clubs and spades, with cards numbered from 1 to 9 in each suit. Each suite, right? Yeah. A hand is a collection of 9 cards which can be sorted however the player chooses. How many 9 card hands are possible? Okay. So let me explain the problem to you guys, and I don't want you guys to solve it, but there's a difference with respect to what we have learned so far, and that's what I'm trying to emphasize. The question says that you have a suite of cards. You call it suite or suit? Suite, right?
Sweet. Yeah.
Suite. So you have a suite of cards. You have 39 cards, 36 cards, sorry, which comprises of 4 categories: hearts, spades, diamonds, and clubs. Okay, and every suite has 9 cards numbered from 1 to 9. Okay. So it says in how many ways you can distribute the card. A hand is a collection of 9 cards which can be sorted however the player chooses. How many 9 card hands are possible? Meaning you have 36 cards. Okay, so this is, let's say this is heart. This is spades. This is diamonds. And this is clubs. Every category has 1 to 9 cards, numbered 1 to 9, which makes 36. Now it's saying a hand, meaning when you give cards to somebody, that person holding the card, that's called a hand. I have this many cards in my hand. So a hand comprises of 9 cards. It's saying how many hands, how many possible hands you can create out of this. And there's only one answer that you guys can tell me after thinking a little bit about. Did everybody get the question? Dev, Shiv, Om, Sahib, Aj. Again, I'm repeating myself in a simple way. I have 36 cards in 4 categories, numbered 1 to 9. Okay. The question says, a hand comprises of 9 cards. It could be any combination of this. How many hands are possible? Yes, Shiv.
Well, the amount of categories and the amount of cards in each category are irrelevant. But you only need to know the amount of cards and the amount of cards per person. So I used the amount of cards in 36 and divided it by 36 factorial. Divided by 36 minus 9 factorial because it's 9 cards per person. And so it would be 36 factorial divided by 27 factorial if you're using that formula.
Okay. That was one start. Let's see what David has to say.
I'll say he's wrong because this isn't permutation because you said they can. You never said they can't repeat. You said they can arrange it in any way.
Right. That was another point. In the question, if I read that line one more time, the line says, a hand is a collection of 9 cards which can be sorted however the player wants, a player chooses. So the immediate indication for us is order doesn't matter.
Combination.
It is not permutation, it is combination. Now, the response I was expecting from you guys was that, sir, you have not taught that yet. This is not permutation. And I want you guys to be brave enough. If I teach you pre-calculus and ask you questions on science, you should be brave enough to say, sir, this is not something that we have learned yet. I don't mind learning it, but we have not learned it yet. Or you have not taught it. So anyway, but yeah, that was more like a wake-up call for us. To switch from what we have seen so far, which is permutation, where the order matters, to another territory where the order doesn't matter, which is called combination. Now let's look at some examples here. Let's say let's not look at a big number to begin with, okay? Let's go back to our same theory of 3 chairs, 3 people, okay? I mean, that makes it easy for me a little bit from a showcase point of view. Let's say chair 1, chair 2, chair 3. And we have 3 people, A, B and C. Everybody with me? So Shiv, I'm not saying that what you said was wrong. What I was saying was my question was wrong. Okay? I mean, I was not supposed to ask that question because I was just trying to see the transformation from permutation to combination. As soon as there was a sentence saying where the way a hand is organized is left to the player to choose. And actually it doesn't really matter. I mean, if you have seen anybody playing cards, it doesn't matter whether you are putting the card in first place, last place, middle, anywhere, right? So that's where it comes into, it moves from permutation space to the combination space, where the order doesn't matter, yes.
Is the card question, does the numbers matter?
I'm sorry?
Do the numbers matter?
Number matters, right? I mean, see, how many cards everybody will get?
The number on the card, because then each card will be different.
So see, again, the way you have to look at it is, these are unique cards. Let's say, if you're talking about a 9 of spade versus 9 of club, they are unique by itself. They are totally unique. They have their own identities. They will not mess with each other. Right? What you can do with a club of 9 versus what you can do with a club of, 9 of spade versus 9 of heart are different. So, from a mathematical calculation point of view, for us these are 36 unique cards. Okay? Now, rule of the game could be different. We are not going into that. But here I am saying, we'll have to treat them as 9 unique cards. Is that okay? I mean 36 unique cards. Yeah? Even if the numbers look the same, but the category makes it different from each other. Yeah? Yes, Shiv.
Sir, I understood the mistake first. So now I'm thinking maybe for now if you're doing categories, would that mean combinations? Does that mean we can also add the amount of categories into question itself?
Right, so let's hold it for a little bit. Let's go back to what I was trying to explain, and then we'll try relating that, okay? So now I have, is that okay, Shiv? Okay. So now going back to the same original problem, 3 chairs, 3 people. Let's look at the permutation options. We're talking about first chair being filled by A, then B, C, A, C, B, B, C, A, B, A, C, C, A, B, C, B, A. This was my permutation option. That is where we said, okay, 3 people, factorial 3. Now, if the order doesn't matter, if the order did not matter to us, this and this, all of this would have been the same actually. All of this would have been the same, right? Everything was ABC, ABC, ABC. If everything was the same, if the order did not matter for us, these 6 things that we see here would have translated into 1. Yep. Probably I took a wrong example. Let me do another one. Let's say this is getting a little confusing. So let me say I had 6 people to fill 4 places. Okay. Now 6 people, 1. Am I? Okay. Sorry, my bad. 3 people to fill 2 chairs. Let's go take an easy one so that I don't fill the board. Make it clumsy. So 3 people, 2 places. Let's say 3 people are A, B, and C, and the places are 1 and 2. So first place I could pick A, and then second place I could pick B. First place if I am picking A, I could pick C. First place if I am picking B, I could pick A or C. Third place if I am picking C, I could pick A or I could pick B. So 3 people to fill 2 places. If I look at the permutation, this is my permutation, right? How many options I have? 6. Yeah? Is that making sense?
Yeah.
Or let's look at it. First place I could fill by 3 in 3 ways. Second place I could fill in 2 ways. So that gives me 6. Even if I look at the permutation formula, 3p2, it gives me 3 factorial divided by 3 minus 2 factorial, which is 3 into 2 divided by 1 factorial, which is 6 again. Now, what we are saying is, here you should look at it carefully, between these two. Between these two. This combination are unique. AB and AC are unique combination. But what you will do is, let's highlight them with different markers. If you look at AB here and BA here, both, if you look at combination, when the order doesn't matter, we are talking about one option only. Similarly, if you look at AC here and CA here, these are only one combination. If the order doesn't matter, these two are not different. Yeah? Similarly, if you look at BC and CB, they are the same. I'll let you guys process this a little bit, okay? I'm just repeating myself so that this goes as deep as it should. I had 3 people to fill 2 positions, okay? And by doing this permutation in the manual way or finding the approach, first position 3 people, second position 2 people, 3 into 2, 6, or applying the permutation formula, 6 is my option. And this is my permutation option, meaning when the order matters. Now we are trying to find out combination, meaning as long as I have my combination matching, the ingredients matching, be it which one is coming first or which one coming last, doesn't matter. Then I'm able to actually minimize the number of combination. My combination will be less than my permutation. By how much? It's less by how much?
You did this in this one,
I'm sorry?
in this only situation,
Yeah, in this situation.
3 times less.
3 times less or half less?
Wait, compared to what?
See, my permutation was this many, 6.
Oh my god.
Now, we found that we have duplicate for every combination. Okay? So, AB and BA were duplicate. I will not count them twice. I will only count them once. Similarly, AC and CA I will not count twice, like the way I am counting for permutation. Because for combination, my order doesn't matter. Similarly, CB and BC I will not count twice. I will count only one. Meaning, whatever I am getting for permutation, let's say, I got 3 out of 2, okay, 3 things to fill 2 places. I got 3 factorial divided by 3 minus 2 factorial. This was my permutation option, meaning when the order doesn't matter. What I am coming to is, oh, I have, if I divide that by 2, this is my combination. When I'm discounting the order. How many permutations I have? 1, 2, 3, 4, 5, 6. Now, how many combinations I have? I'm joining them together. I have only 3 divided by 2. Similarly, or the other way you would look at it is, okay, now let's look at another situation. If, let's say you had, what you're saying is, I don't want to count things multiple times. If for me order doesn't matter. When I'm talking about combination, for me order doesn't matter. Meaning, what I have extra is how many times those things are organized among themselves. If I have 3 items in my combination, they are organized among themselves in factorial 3 ways, correct? That's the way I can juggle them or arrange their orders. I don't want to count that part. Or if I have counted that order part, I want to eliminate that. And how would you eliminate that? You will say, okay, I don't need that part. So this is the total number of permutation I have got, and all the counting that I have for rearranging them among themselves, that part I want to eliminate. Again, now let's look at it. Who all are confused? Everybody. Let's be confused. At least we're trying to understand something. That's fine. Now let's look at a situation, okay? I have, let's say, look at this option itself, okay? How many cards we have? 36, yeah? We are trying to find out combination of how many combination of hands we can have and every hand has 9 cards. Let's assume that order matters. Then I would have used the normal permutation method and I would have got 36 permutation 9. That is how I would have chosen. That's how I would have chosen 9 cards out of 36. Yeah? And that would have given me 36 factorial by 36 minus 9 factorial. Yeah? What is extra here?
The fourth
All the people that they have the cards in their hand, I'm counting how many ways they are arranged among themselves also.
Yeah.
Because I'm talking about permutation. Oh, this one is 1, okay, 1, 2, 3, 4 and up to 9. Oh, 2, 1, 3, 4 is another one. 3, 1, 2, 4 is another one, and likewise. all the possible ways in which they are arranged among themselves, that also we are counting, which is not needed in this case. Because we are told that we are leaving that to the players to choose how they want to arrange the cards. So you are picking nine bundle of 9 cards from out of 36 in any which way without bothering about how those are arranged. Right? I mean, the way we were making 7 people sit on 3 chairs, said A, B and C, C, D, E. Okay, sorry, let me not confuse you guys. 7 people on 3 chairs. Chair 1, 2, 3, these are chairs, okay? I'm saying person A, B, C. I could have B, C, A. I could have D, E, F. I mean, A to 1 to 7, I'm saying A, B, C, D, E, F, G, right? So here, if I had A, B, C or D, C, A, these were counted in case of permutation. The order was getting counted. Here, when I'm picking the cards, how many ways the cards are arranged in the hand, we don't really need to care about it. Because my permutation always says that the order, this one first or this one first matters. In case of card, this one doesn't matter, meaning we are counting all the scenarios, how they are arranged. Let's say if I had 9 cards, I am counting the factorial 9 ways also in my actual permutation. If I divide it by that, the juggling that I am doing with the 9 cards among themselves, that part is ruled out.
I'm starting to see the formula of combinations.
So again, let me hear Dave and Siv also at home. Am I making sense a little bit? A little? Very little?
I mean,
I'm sorry?
barely.
Barely? Okay. So, okay. Now let's think reverse. Okay? Let's forget about what this question was. The question was saying that you have 36 cards, 36 unique cards, and you can choose 9 cards. Create hands with 9 cards. How many ways we can do it? 36 P9. That will be my way to pick up 9 cards out of 36. Yeah?
Yeah, as you said, 36 unique cards. It's the ice cream shop.
It's getting me tempted to buy ice cream. Okay. Alright. So coming back to this one. If I had 36 cards and I had to choose 9 cards, how many possible ways I could choose them? 36P9, permutation of 9 out of 36 options.
Yeah, because you said 36 unique cards.
They are unique cards only, right? Every card is unique.
Yeah.
And every card is recognized by 2 things, the number on it and the category it belongs to. So that is how every card is unique. Yeah? So these are the ways I can find 9 cards. These are the ways I can make a hand of 9 cards. Is that okay? Yeah? So I have 36 cards, I am trying to pick 9 cards. These are the ways. These are permutation ways I can find out a hand of 9 cards. This will be 36 factorial by 36 minus 9 factorial. I am saying this is okay as long as my order matters. Whether I am picking, I have 9 cards in my hand. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth. 9 cards I have. Which card, let's say, I am holding 9 cards right now, okay? 4, 5, 6, 7, 8, 9. Yeah, I have 9 cards right now in my hand. Okay? Whether this card is first or this card is first, doesn't matter to me while I'm playing the cards, right? But here in this case, when you are doing the permutation, it actually matters. You are taking that into consideration, saying, okay, fine. How I have got 9 places in my hand filled, it actually matters to me. So you are saying that, see, here in this case, first place you would have filled in 36 possible ways. Second place you could have filled in 35 possible ways. Third place you could have filled in 34 possible ways. Fourth place, fifth place, sixth place, seventh place, eighth place, and ninth place. And you would have multiplied that to get the answer, which is same as this one.
Yeah.
But when you fill the first place in 36 possible ways, you were counting, okay, first place is this one. You are counting this one in the first place, then looking at this combination. Counting this one in the second place, then counting all the combinations. I'm saying this, how you are arranging these 9 cards among themselves, that is also counted in this whole thing. Or, okay, let's take a simpler example. I know this concept might take, how much time we have?
I have a question.
Yes.
So, since you're arranging it in a specific way, would the combination would be just 36 to the power of 9?
Say that again?
Would the combination just be 36 to the power of 9? If it's not in a specific way?
Yeah, if it's not in a specific way, then that will be simple, right? A brief position you can fill in 36 ways. And will it be 36 to the power 9? No, it will not be 36 into 9, right? Because when you are, okay, let's come to that, okay? I'm still not thinking about it. I'm still thinking about how do I make it look easy to you guys, okay? Let's go to, okay, I'll take 5 minutes. I think we are already over time, but let's take 5 minutes, okay? Let's say I had 36 cards and I had to choose 4, okay? Make a hand of 4. How many ways I could do it? 36 factorial divided by 36 minus 4 factorial. Yeah?
Yeah.
What that would have been?
36 times 35 times 34 times 33.
That would have been my answer. Now let's say I got, in the 4 options, I got A, B, C and D. These are my 4 cards.
Yeah.
It could be anything. Now, when I got this many options, I got, let's say A, B, C and D. These are my 4 cards. How many ways this can be arranged? A, B, C, D, A, C, B, D, A, C, D, B, and A, B, C, D, A, B, C, D, okay, A, B, D, C. So with A only I have 4 options.
Yeah.
When I put B, C, D, I will have certain number of options, okay. So, and it comes down to how many ways I am able to arrange A, B, C, D among themselves.
Yeah.
And that is what? Factorial 4. I have 4 things here. I can arrange them in factorial 4 ways. But do you want to count all this in your hand?
No.
You don't want to. So what you are double counting is how you are arranging it in your hand, and that is being ruled out. So whatever you have already counted in this one, that you want to discount. And how do you discount that? By dividing. Say, okay, fine. I have double counted this because I assumed the order matters. I want to rule out those options. So every combination I'm getting, within that, whatever organization I'm doing, that part I want to discount or rule it out. Shiv, Dev, Om. Is it getting little closer? Little closer. So okay, let's not try rushing for understanding permutation and combination both in the same class. Permutation part, at least we are clear.
Yeah.
That we have certain options to choose. We looked at the permutation formula. We looked at how do we choose different options, and we played with that. Combination, we just got to understand, okay, when the order doesn't matter, that is what is combination. When whatever reorganizing of things that I do inside that part doesn't matter. That we have to rule out. How do I represent that? Let me think through that a little bit more, and I'll try breaking it down for you guys in the next class. Okay, because this is going to be our base for probability. Okay.
Yeah.
Permutation combination. If we are very clear, it'll help us play with probability in a much easier, better way. Okay. So I'll treat this as an opportunity for me to kind of simplify this from an understanding point of view in the next class. Is that okay? And then we'll look at the combination concepts one more time, and then we will start moving towards probability. Will that be okay? Applying these two? Okay. With that being said, I'll let you guys go. I know everybody is stressed out and hungry, and let me find out some easier, interesting way for decoding this. Yeah? Alright?
Question.
Yes, better.
So if you have more